window. Okay. What happened to this GUI? Oh. I don't understand why this happened. Default. Okay. So yesterday, what we did is, okay, so we were trying to, so as you remember, we were trying to um, read something from a data file, right? So binary numbers we are trying to read. So where we put that, I think in version 5. Yeah, yeah, this is where we try to read from a data file. So we use the read table command. So binary numbers.xlsx is what we used. So there's another command actually, xls read. The command called as xls read. Okay, there is another command called as also xls read. Okay, the same. It does the same thing. There are some differences in the algorithms of each function, but essentially they will do the same thing. XLS read will create something will create an object of some data type, whereas read table will create a table object. So we saw that when table object is created, I was not able to index it. So the reason was that the table object is different and matrix object is different. So you cannot just index a table object, you have to convert it to matrix. So let's run this, how it, let's see how it, first let me show the logic is right. So we read some numbers, then we, for I is equals to 1 to size, again I explain this, how from I to I is starting from 1 to this 3, and j is equals to 1 to 4 goes. And I said that if j equal to, so first and third column, they're unsigned integers, whereas second and fourth column are signed integers. And then the corresponding to I and j, just the j values, signed variable. I mean, this variable signed will take its value false and true, and will go inside this, and call this function convert to convert binary to 2D, and here we get the result. Okay, so let's just run this, and the error is that you cannot index it. Yeah, length for input arguments of table type. I mean, indexing also is itself the issue, but the length is not applicable to table type arguments. Okay, so this is what it is saying. So what we can do is convert the binary matrix to, so let's modify this a little bit. Binary table and binary table, binary table. Okay. Oh, sorry. We can have binary mat here. Sorry, because we're going to change it. So binary matrix is equal to, what we'll do, use the function table to array, binary table, binary table. Okay, so this is how we create a binary matrix, and then now we can do that. So let's see what happens. Okay, there is now some issue. So yeah, I was actually hoping to have some problems so that we can see what is going on. How to debug is also a procedure. So now see how I can debug is that I need to see what happened when I was trying to read it. So let us also see what this file is. Binary numbers.xlsx. Uh, yeah. So see, this is the file, and so A B C D X S X L S X 10 or whatever. So the decimal number is NAN, not a number. That means it is not detecting a number there. So we need to see where it fails to detect a number. So what we can do, so total number of it did total number of times this iteration was run is this 1, 2, 3, 4, 5, and 6 times. But it should run. So why is this nan? I don't know. Let me go and modify a little bit. Yeah. Meantime, what we'll do is print out the iteration number so that I can zero in on where the issue is coming up. So see, signed decimal number is 1, decimal number is none. That means there is some issue with decimal number. Okay, so we'll see for I'll print here I and J. Sorry, let's have some annotation so that we can recognize it nice. F printf I value percent I comma J value percent D comma percent D. Now we'll see what goes on, what goes wrong, and we will what we'll see is if this I mean when this loop is being run, if this is the block is being if this is the block executed, then sign should come out false and this should come out true. So we'll also print out what the sign variable is here. This is all a part of debugging. Okay, def sign variable, sign variable. Okay, now let's just, since it is a true, let's just print out signed. Okay, and let me go and modify this XLSX a little bit. Editor, run this. Okay, see now the input is coming up and we are getting a little bit of information on what is going on. So IJ value 1 1 signed equals to 0. So is this happening? Let's see if this happening according to our logic. So J is equals to 1 and so first and third column are signed unsigned integers, right? So signed equals to 0, false. Yes, it is coming out right. And decimal number is NAN. We'll see why it is coming up. I and J value 1, 2, 2, and J is equals to 2. It is taking and it is giving up logical. So signed is equals to 1. So yes, it is working out. And signed decimal number is coming up 1. So maybe there's an issue with this XLSX file and whatever we're reading. So we'll solve that issue. Then the decimal number is nan again. Okay, so for 1 and 4, first and sorry, J is fourth. So second and fourth column are, we know that they are signed, so signed equals to 1. So this is working out. The only issue is with there is some issue with these numbers that we are when we take them and we are trying to convert them, there is an issue. So this is how we debug. Okay, so let me just modify a little bit the XLS file and I'll re-upload it. Binary numbers. I'm modifying it down on my local machine. Okay, so now let me save and upload. So let me delete this. Go delete and add a new one. Right now, what I did. Okay. Now there are three. There will be three rows and four. I think four columns. Yeah, four columns. So decimal number is none. So let's visit this now. So 1011. So binary mat ij. Maybe there is a problem with binary matrix ij that we are trying to see. So let's see. Also print out binary I comma j. Okay. Let's print this run. Okay, so it is coming up right. So it is reading it. It is also reading right, but there is again some issue with our logic inside the function, because whatever we are designed to be operated inside the function, it is not consistent. So now let's see this. Even you can think about it. Okay, just start thinking of what you can do in this. So binary number again. Okay. And the problem with this is sign decimal number is coming up 1. Yeah, the issue is that this binary number, as I said, this binary number is supposed to be what? It is supposed to be a string, right? String. We are taking inside a string, and then when we are processing it, then we are converting it to number. So that is why when we printed this binary mat, you see in command window that it is giving out number. So we need to first convert it to string. How can I convert it? Is that you can just convert this to string. So maybe what I can do is write this inside a function itself. So whenever a number is to be received, I will just a minute. Just a minute, okay. Yeah. So yeah, I'm back. So let's write this inside is that whenever you receive a number, you first convert it to a string. So binary number is equals to, there is a function string, I think. So binary number. So this is how you convert a string. So let's also take help from MATLAB. String. It's in the responsive today. Yeah, so string is there. So see, there are so many functions inside the string. So there are a lot of functionalities available for you to read, but that those are again very specific to your application. So you don't need to be overwhelmed by this much amount of content that it is showing you. Mostly what will happen is when you're applying it to you in your assignments or where whatever your applications are, you'll be looking at some specific command. So yes, the string binary number. Then now let's see what happens. I'll comment this. I'll suppress the output. Let's see. Okay, it is still giving out something different. It is still giving out errors. So convert binary. We did convert to string. I don't know. So okay, just give me a minute, okay? Let's try to zero in on what exactly is going on. There must be an issue with the numbers. So what exactly is the issue? We can also go ahead and try. Okay, it's better to think on it and just see what I'm doing. Decimal number. There has to be an issue with this input. Help string. Let me see what type of output it gives me. String converts a character vector chr into string array. String C converts a cell array C into string array. Each element of C must contain a value that. Okay, so yeah, this is where the problem is. I think we are using strings. We are not using strings correctly. So let's see. There is a function. I think it is num to num. Let me recall. I think it's num to str. Let's see. Num to str. Let's see now what happens. We saved, ran. Yeah, it's coming out now. So yes, so see, for I is equals to 1 and j is equals to 2, which means this one. I is equals to 1 and j is equals to 1, 1, 1, 0. I, j, 1, 2, signed decimal number minus 2. Okay, that isn't true. Signed decimal number is 1008. I think something has been solved, but not everything. So we know 110s. So first and what was the condition? Yeah, first and third column are unsigned, right? So 110 should correspond to 6, but it is giving out 11. So again, there is an issue. Num to str binary number. Okay, I will have to spend some time on this. So what we'll do is I'll see exactly. I didn't plan to. I mean, I was hoping to have some error, but I didn't expect this another one to pop up. I was under the impression that string will actually do the thing. But I will let you know in the group after the session, because let's not consume time from this. So basically, I just wanted to give you some sort of a debugging procedure to know to where the problem occurs. Okay, so what I did with the printf. So that is why I wanted to see where the value is. So first I checked whether there is some problem with the signed variable. Then so for that I use the I see this fprintf actually gives me where I am in the current iteration. So every time I and j prints out, I know what the iteration is doing, and so I can point out where the issue is. So then we printed this out. Then we printed the signed value because I wanted to know whether it is coming out right. Then we saw that this is there. There is no issue in this, but only issue after this line, right? We saw that this after only this line gets executed, the problem arises. So that is where we zeroed in that okay, this might be the issue, that binary number here and binary number what we're giving is a little, are both in different formats. So that is why we were doing something wrong. So if you go to version 4, we were just running this convert to binary. In that case, we were entering a binary number directly. So um, in the form of string, if you see here. So that is what we are trying to do here, but I think there is some other issue. I will try to see what it is. We are actually already trying to give a string to this binary number, but it is still not working out. So we'll see what I'll see what this is, and I'll let you know what the problem was. But the crux of the this demonstration was that how you can debug in a very uh, rough, I mean, very basic sense. How you can debug the code. So now the thing is, now try to cover something of the advanced topics of the MATLAB, like for example, linear programming solving, or let's say, okay, so there are optimization toolbox in MATLAB. So optimization, whatever you have studied while you were studying for GATE, like linear programming, then you can, I mean, you there is a separate toolbox and separate environment for MATLAB in MATLAB to do that. We'll see what that is. Then we'll see symbolic toolbox. This is again very groundbreaking, kind of a very popular technology in MATLAB that they offer. So symbolic differentiation, symbolic toolbox contains symbolic differentiation, symbolic integration, symbolic equation solver. So we'll see that. Then we'll see how to solve differential equations using ODE 45. This is very popular, and you'll be hearing it a lot when you're doing your assignments, because it is a very popular differential solver, and you probably know the mechanics behind it because it's based on numerical differentiation, and that you already have studied. So it will be very intuitive for you to study that. So we'll see that also. Then what else I have planned? To give you a certain information about curve fitting, uh, like for example, least squares curve fitting. So we give a function. So if there is a function and a data is given, so basically, if I want to fit a data, if I want to fit, so let's say there is a x data given and y data is given, but y data is like an output. Okay, and I am trying to fit some function to it, like in a regression, what you do, the same thing actually, least squares, we are going to use the approach. And LSQ curve fit is a function that takes in these functions, the function that you are trying to fit, the polynomial you're trying to fit, and the y data, and gives you a nice fitting polynomial. So we'll see that too. Okay, uh, can't see any image. Are you able to see my screen?
Yes, so I can see
Yes,
the
yes.
screen share, but maybe because of his network issues.
Yeah. So okay. So I am presenting the screen. So okay. So now we'll go on to that. I'll notify you of the error that came in this problem. It is not a big some sort of a big error. We'll try to cover that. Okay. So now let me go and create new live script for now and start discussing this. Okay, so right from symbol, so we'll start with symbolic toolbox first, because this is much more important than anything else. It gives, as a researcher, it gives you a lot of flexibility in solving equations and stuff. So you don't have to sit with your pen and paper every time you want to solve an equation. Okay, and you don't have to even go for numeric differentiation every time, because even numeric differentiation contains all the parameters like deciding the tolerance and the errors, then in the starting point, guess points, and all everything that is needed to solve a complicated ordinary differential equation is needed to be input to the numerical differentiation toolbox. So that is why we'll first see symbolic toolbox, and that is, it's like this. So we first define. So let me save this first. Take away S4. Okay, so yeah, so sims is the keyword here. So we put sims here, then we define the variables that I want. So okay, you won't understand by this method. So let's say I'm trying to solve an equation. So let's say, so since we are starting with differentiation, let me get rid of this and write text here. First is symbolic differentiation. Okay, so in this differentiation, so let's say I have some function and that I want to differentiate. And what that function is, let's say f is equals to e raised to x cos x. So e raised to x times cos of x. This is the function that I want to differentiate. So this is so you probably have known numerical differentiation only up till now, and that you will have to do all sorts of stuff for this, providing the initial guess points, the absolute tolerance, and all. But Symbolic Toolbox does that for you very easily. It's not actually the numerical differentiation; it is entirely different technology. So see, Sims x yx, because this is my symbol. X is my symbolic variable here. So symbolic variable, what I mean by that is I won't put any value in that. So whatever the way exactly what we do on pen and paper by using these variables instead of values, what we do is what symbolic toolbox will do for us. So now symbolic x will put symbolic x first. We define that x is a symbolic variable. Now I'll define the function f is equals to ex into cos x. Then I'll define now differentiate now I want to differentiate this. Okay, so I want to differentiate f and I want to store it in a variable y. Diff of f. Okay, so let's see what happens. See, it gave us the result. It's that simple. It just gave us the value what we wanted. And now let's say you want to solve it to the end. So for example, you want to solve it. So for example, you want to substitute the value of x now. So obviously now, since you have gotten the result, you can also do that by literally taking y and putting x values. Okay, but since it is a symbolic variable, now everything is being operated inside symbolic toolbox. So now what you do is use something called as substitute x value. Now substitute will ask where do you want to substitute. So I want to substitute something in y because this is the relation where I want to substitute. So y is substitute something in y. What do you want to substitute with? I want to substitute x with, let's say, 3. Okay, so this is the substitution syntax. So first argument, what do you want to substitute in? X means what the variable is that you want trying to substitute, and the next argument is the value that you want to substitute with. Okay, so now, but if you see, let's see what happens here. See, this is what happens. So it has just substituted. That means it's replaced these values by 3, and this is also sometimes needed for you guys. So because if there was two functions, so e raised to x cos x, let's say, and e raised to y cos y. Let's say there was this function, then I wanted to know. So let's say if I had just one value, that means I wanted to substitute value of x. Then I need to know what it looks like this. So this is one step, and then what we can do is store this result into y substitute, and then take VPA of it. Variable point arithmetic. That means it now calculates it. So y substitute. Now let's see. Okay, so it will give it an answer, and variable point arithmetic actually gives you the arithmetic. I mean the calculation to a very large decimal. I mean the large precision. I think it's double precision. It may be even more than 16 digits. So this is needed actually because when you're trying to compare with differential numeric differentiation results, you want to know what the error is. Okay, sometimes the errors need to be very small in the orders of 10 raised to minus 9 or something. So in that sense, VPA variable point arithmetic calculates your substitution, this particular uh, equation, and then gives you a result in such a large the precision, such a high precision. Okay, so let's see one more. Let's say, so what we can do, okay, yeah, so now there is another thing, a double differentiation. So right now you differentiated once, so there's another thing. Let's see, y2 is equals to diff f comma 2. So by default, when you substitute, when you put f here, it is going to differentiate once. Okay, it is going to differentiate just once because there is a hidden one inside this bracket. we don't see it. And now that I provide 2 here, it will now differentiate twice. So let's see what that means. So see, this is double differentiation. When you differentiate this, you get this. Okay. So if you differentiate this, now if you do a substitution, y2 substitution is equals to subs. What you want to substitute in, now you have to substitute in y2, not y. And what you want to substitute, x, and with a value, let's say 4, and put a semicolon just to avoid printing, and then vpa y2 substitute. Okay, so this is the answer we get. Again, a very large precision. So okay, so is this clear now? How to use symbolic toolbox? And yeah, one more thing. There's something called as differentiation of constants. So uh, let's say your differential equation contains something like this: e raised to x cos x plus some constant, or anything whenever a constant comes in into your function. How do you differentiate that? So it needs to know, the symbolic toolbox needs to know that this is a symbolic constant. Symbolic constant means that, like this. So for example, c is equals to sim 5. What this means, what this means is that now I'm defining c to be a symbolic constant. So now if I differentiate c, it should give out 0, shouldn't it? So let's see. C answer is 0. But if I hadn't done that, let's say d is equals to, let's say 2. Let's see what happens to diff d. It gives an empty values. Why? Because it doesn't understand that d is in fact a symbolic variable, and that diff function, or this diff function belonging to the a symbolic toolbox, needs something that is symbolic inside it. So whatever you're putting inside should also be symbolic for it to understand. Okay. What else in symbolic toolbox? Okay, so one more thing is the fact that let's say you want to have, suppose there are two variables inside the function, and you want to partially differentiate with respect to one of the variables. So now what you will do is this: you define the another variables. Now this was for okay, so this is for one variable. Multi variables. So now again, sims, let's say there are R and S variables. So sims rs, then define the function, whatever your function was. Let's say g is equals to cos of, let's say, rs maybe. So cos of rs, so it's like cos of xy, but I'm not using x here. Rs. So now this is the function I defined. Now again, so now you differentiate w is equals to diff g. Now you have to specify which variable you want to differentiate with. Okay. So now I'm saying that I want to differentiate this with respect to r only, and double differentiate, or let's say don't differentiate double right now. So this is the differentiation. Now let's see what happens. See, it differentiated with respect to r. It differentiated with respect to r and gave us this value. If I wanted to double differentiate this, I'll just provide another comma here, comma and 2. 2 stands for second time differentiation, and there is a 1 hidden. That's why I didn't put 1. And so again, a square cos rs. So you can go on about that, and then maybe let's say, so this was d. So this was like del g by del r. Now let's calculate. Okay, let's w r, then ws is equals to diff g comma s comma 2. See, so see, this is what you get, obviously, and then now what do you how would you substitute this, right? So substitution again. So well, I'll combine the two of these commands. So why substitute and this there is no need to store it in the one variable and then use it. You can directly use like this VBA substitute. What you want to substitute in? You want to substitute into G. No, sorry. You want to substitute in what WS. So let's say you want to substitute in WR. What do you want to substitute it with? Let's say I want to substitute with no. So let's say I want to substitute both of these values. So R and S. So I'll create an array there itself like this into square brackets 1 space 2. Okay. So let me first actually in the array I'll have to specify what is to be substituted, right? So R comma S and then into bracket let's say 2 comma 4. So this is what I want to substitute and I'll get the answer now. See, I'll get the answer. Okay. So yeah. So I think that's it for symbolic toolbox for differentiation. We'll move on ahead to differential equations also. But before that, we'll take some questions if there are. Anybody? No questions.
Please again explain the VPA syntax.
VPA syntax. VPA syntax. To see why I did two steps here. VP y2 is substitute is equals to subs, in which I stored this substitution variable into y2, and then I took VPA of this. So VP is a function which can take directly this value, right? So previously I'd stored this whatever I've highlighted into some another variable, and then use that variable inside VP. So now instead I'm just using the variable, I mean the variable itself without actually storing it in something else. So VPA parentheses and close parentheses. Look at it like this. So VPA opens up and just is like this and is ready to accept something, and I put this in here. So now it will do substitution into this and calculate VPA.
Okay, thank
This function is same for single variable and even in partial differentiation. How does MATLAB differentiate? So how does MATLAB differentiate is by using I mean this second variable R and S. So diff. So see when I type diff f, it by default assumes that the so depending on the nature of the function, it automatically gets to know whether the function is to be differentiated partially or not. So now in this case, I defined cos rs, and now I'm defining r. So the next argument is telling diff function to differentiate with only with respect to r. So here you don't have to specify here. If you even if you specify, it already knows that anyway there is only one variable there. So if there is only one variable, I'll differentiate with respect to that. As soon as we give two variables, it needs to be given what variable it needs to be differentiated with respect to. But as you will explore ahead on your own, you'll also get to know that MATLAB sometimes decides on its own. If you let's say if you not specify this r, so there is a condition called as I don't know the specific word, but it's like it decides its closeness to the x variable in alphabet. Like for example, in alphabets, uh, s is closer to x, right? So there's some kind of a where this rule set up inside MATLAB so as to not give errors while running long codes. So it will just take this and substitute and differentiate it with respect to a variable that is closer to x in alphabets. So if I don't substitute r here, it will differentiate with respect to s directly. Anything else? I hope I cleared your doubts, Saurabh. Okay, so I'll move on now. So now, since I put symbol, okay, symbolic differential symbolic differential equations. Okay. Now, differential equations. So first of all, I'll need to define the dependent variable and the independent variable. Now, at first, we don't have to explicitly define that this is independent and this is dependent. There's no syntax for defining these such kind, but we'll define it when we are using the diff function. So now, let's see. A differential equation we'll use like this: diff dy by dt at dt is equal to t into y. So this is the differential equation we'll see. Very simple. This is an ordinary differential equation. Dy by dt is equal to ty. We'll try to solve it using dsolve or symbolic toolbox solving. So obviously there are differential equation solvers out there, but we'll use this now because it's very simple and it is very easy to obtain results for some of these problems. So I'll also tell the limitations of this at the end. So okay, so how do we do that? Code. Again, the definition of sims, let's say, I don't know, y of t, and t. So I defined two variables. One of them is independent, another is dependent. Doesn't matter the sequence. I'm just defining it yt and t. Okay, so this will be our independent variable and yt will be our dependent. And so let's define an ODE now. ODE, let's say ODE first. This is my own variable ODE first. Okay, it may confuse you maybe for first order. ODE1 is equals to. Now, in order to get this dy by dt, I'll use this as syntax. Diff of y of t, comma t is equal to t times y. So this is how you define an ODE1. This is a syntax given by Symbolic Toolbox. So even if you see that there's an assignment operation here and an logical equal comparison operator here. So even if that is the case, this is the syntax defined by MATLAB while solving symbolic equations. So whenever you're using diff, you have to specify the RHS. So this is RHS and this is the LHS. So diff, you can see here the dy by dt is diff y by yt by t, and since it's a symbolic thing, so earlier what we were doing is differentiating it directly, because if we were knowing the function f directly here, f is equals to e raised to x cos x, but since it's a symbolic, we don't actually have to know exactly what it is, and so we directly write diff of yt comma t is equals to ty, and let's see what it gives. See, it gave us this, in nice formatting, it gave us d of yt is equals to tyt. So let's comment this and let's solve this. So solution is like solve1 is equals to dissolve, it's resolve ODE1. Okay, so let's see the result. And yeah, this is the equation, this is the solution to this differential equation, c1 e raised to t square by 2. So c1 e raised to t square by 2 came up because we didn't specify the initial condition to it, and if when there's a method to define the initial conditions, and then we can get rid of c1. So remember, desolve takes ODE1, whatever you want to solve. So we created a differential equation, this. So consider this as an RHS, and this RHS, the ODE we stored in this variable ODE1, and put the ODE1 inside this desolve command. Now again we can use VPA, substitute inside solve1 with, let's say I want to substitute t with 1. Let's see. See, it's still giving C1 because I haven't specified initial condition, but it evaluated this value. Okay. So VPA substitute solve1 T1. Now there is a method of giving it the initial conditions. So let's say, so in order to complicate a little bit, we'll use double differentiation and then use the two conditions, right? You'll need two conditions to solve, right? So since it's a double differential equation or second order differential equation. So how do we do that? Is like this. Let me just, break section. Sims y of x x and will now you define the ODE1, sorry, ODE2 is equal to first I'll so let's say the differential equation is this. I'm sorry, I forgot to write this here. Second order ODE. Let's say it is like D2y, and now I will not be able to write it cleanly here. D2y by dx square dx square is equal to cos of 2x, let's say cos of 2 times x minus y. Okay, so let's say this is the differential equation. So now how do I double differentiate? So let's first start by differentiating it once. First, inside I will create this ODE and note how I create it. So I differentiated diff of y of x with respect to x first. Okay, so I created dy by dx. Now let's just again, if I want to again differentiate it, I'll just put this inside another diff. So one more diff, and that's it. So inside this diff, I put another diff, and that's why that is how it came out to be d2x. But still, what is happening is, see, as I paste it, I just pasted the differential equation. Now again, I want to specify with respect to what. So again, it is with respect to x. So note this. So differential equation, define the differential with respect to x, and then put this and differentiate with respect to x again. That is what will give you d2y by dx square, and is equals to so double equal to cos of 2 into x minus y. Let's see. So it gives us a nice result now. Okay. So now the pending condition is now that we have to specify this initial conditions, right? So initial condition is like, let's say y of 0 is equals to 1, y of 0 is equals to 1, and y of, sorry, dy of, so y dash of 0 is equals to 0, let's say. So considering this, y dash of 0 is equals to 0. Now y dash of 0 is equals to 0. That means we need to differentiate y, right? So let me modify this here again. Let me say dy is equals to diff of y. Okay. This creates us the y dash of y. This creates a y dash value. Okay. So when it creates a y dash value, I mean, this creates a differential variable, differential data. I mean, differential object here. So now we'll feed this. I mean, we'll equate. I mean, we'll create this initial condition and put it into solver. So how we'll do that? It's like this. Condition one. Condition one is equals to condition one is that y of 0 is equals to 0. So y of 0 is equals to 0. Sorry, 1. And condition 2 is dy of 0 equal to 0. And now what I'll do is concatenate those conditions into const condition 1 and condition 2. Condition 2. And now I'll feed this to solver. So solve, let's say solve ODE2. Solution of ODE2 is equals to desolve. What do you want to solve? ODE2, right? ODE2, comma, conditions or cons. There it is. So now if you run this, see here, solve on ODE2. See, it solved it for us and so much nicely. So this is what Symbolic Toolbox does for us. Let me see questions. Is it necessary to specify YT as symbol, or have you selected it for understanding? Which one? Okay, you're referring to this YT. Okay. So if you specify this, it's actually helpful. Okay, so it's for your understanding itself. So by default, when you're differentiating, it will associate this with this that this will be the dependent and this will be independent. So this is for your own, our own understanding as a programmer. VPA substitute. So I'll substitute this solution of ODE2 with, and I'll substitute x value with 2. It will give me an answer directly. Solve the unrecognized variable. Solve, where is it? Okay, ODE2. Okay. So are there any other doubts in this?
Hello.
Yeah.
So I'm on 25th line. Inside the differentiation, there's one more diff y of x. So instead of that, is it okay if we use dy symbol?
dy? Sorry?
On 24th line, you have already defined a dy, right? Dy.
Yeah. Okay.
Is it okay to use that value in 25th line?
Let's see that. We'll see that. See, it is not allowing us. Invalid expression when calling a function or indexing a variable. Use parentheses. Otherwise, check for mismatch limit delimiters. I think there is some issue with this dy.
I think you should erase comma x in that bracket.
No, because dy. Yeah, it is giving the same answer. Sorry, yeah. So you can use this, right? Right, yeah. So dy actually creates a dy by dx variable. That's right, and that is why you can just substitute dy. There's another option. You can also use this one. ODE2 is equals to diff of, let's say, y, comma x comma 2 directly. X. Minus y. So you can, let's see, try to use this. See, we'll get the same thing. So you can also use this. So basically what will happen is, if you're solving a fourth order differential equation, then it will just lengthen, right? It will become so much longer. So that is why actually I wanted to tell you I told you this, and then I was going to tell you this. So diff of yx with a double differentiate. So I'll specify 2. If it was 3, I will specify 3, and so on. So yeah. So any other questions in this? Solving
if it is
differential
second degree,
higher
can
order.
we just hello?
Sorry. Yeah.
If it is second degree, can we just put the power 2 at the end?
Yeah, that's what I've written here. That if you want to differentiate it twice.
No, I'm not asking about.
Okay.
Yeah,
Yeah, second degree. Yes. You can do that. You can just do this bracket this and square. You can do this. Right, I got it. So you can do higher degree differential equations too. But what happens is that sometimes when the orders, I mean, the differential equations become complicated, symbolic toolbox actually takes a lot of time to converge. I mean, there's no such even thing that there's a convergence. It's actually mainly observed in numerical differentiation. So sometimes OD, so this symbolic toolbox might not give you an answer, or will give you an answer that is wildly inaccurate. So that is because the functionalities of symbolic toolbox are being exceeding, and so that is when you'll use the numerical differentiation. So this is for maybe for prototyping and seeing and visualizing purposes. Anything else? So shall we go ahead? We'll go ahead. Okay, now let's also see symbolic integration. Okay, so what is the plan here? There's symbolic integration, then equation solving, then OD45, then linear programming and LSQ fit. Okay, we'll have to cover a lot of ground today. See, symbolic integration now. Text. Symbolic integration. Let's see, my function that I want to integrate is x square plus y square, or x cube plus y cube. Let's say f is equals to x cube plus y cube, and I want to integrate this. Okay, so integration. So I'll integrate this directly here. It's integration is even more simple to write. So sims, I don't know, I should define a little bit differently. Let's say q, sims q, and sims q r. I'm sorry, then this also gets modified, but you get the point. Sims q r g is equals to the function q square, sorry, q cube plus, and I just want to integrate this function with respect to q. Okay, so this is double. This will require double. So let's first cover only single one. So x cube is what I want to integrate. Let's say cube. Okay, so now I'll just put int comma g comma what q, and I'll get the answer. It's very simple to write int g with respect and integrate with respect to q, but by default q is the variable to be integrated with. So even if I don't specify this, it will still do the same. Okay. Only when there is an ambiguity in differentiation, like if there are two variables, only then you have to specify what variable you want to differentiate it with. Integrate it with. So now, so this is very simple. Let's include the q and r part. Plus r cube plus r cube, and now I want to double integrate, right? Double integration first with respect to q, let's say, and then with respect to r. So first I'll integrate with respect to q and just put this inside integral and this with respect to r. Okay, so now I'll integrate. So see what we got the resulting answer, and now we'll just get VPA substitution. I think I'll have to put this into some variable. Int result is equals to this, and substitute into int result the value of, let's say, okay, so q comma r with the values 0 comma 2, let's say. Oh yeah, sorry. Okay, so this is how we get double integration also. Let's take also one more example. Let's say h is equals to q times r. In result 2 is equals to integration of h with respect to first q and then with respect to then r. Okay, and then VPA substitute and result 2, and the values to be substituted are q comma r comma values 1 comma 3. This is just for one more example. So any doubts in this? Again, I don't think many doubts will be there because this is literally syntax playing. There is no logic in this. You just have problem defined in front of you, and you just have to know the the place of the logic. Sorry, place of the syntax. So any other question? Okay, somebody. Okay, please mute. Somebody's mic is unmute. So we're hearing a noise. Please unmute. So please mute yourself. Okay, so now we'll move on to symbolic equation solving. Symbolic equation solving. Symbolic solving the code. So let's say my equation. Okay, so now there are, so let's say there are 2 or 3 equations, linear equations, and you want to solve them. So system of linear equations. That what I mean is that I want to solve a system of linear equations. So let's consider that the number of variables is equal to number of equations for now, and let's say I'll put 2 equations. I'll write down these equations here. X square into x square into y square is equals to 0. Square into y square is equals to 0. And the another equation is x minus y by 2 is equals to 0. X minus y by 2 equals to 0. So these are the equations that I want to solve. Sorry, not 0, it's a, some variable a. Okay, but essentially, since we are solving it symbolically, and so see, you'll get what I'm saying here. So I'll define sims. Okay, the best idea would be now to switch to a new MLX because I'm running out of variables. Okay, symbolic equation solving. This here, I'll insert a code. Symbolic, let's say x, y, and a. And now I'll put these equations. I mean, I don't have to put them differently. I'll just put them inside something called as a solve function. So solve. What do you want to solve? These equations. So just put them here. X square into y square. Y square is equals to equal to 0, comma, and this next equation, that is x, and just equals, and close the bracket. So now you are ready to solve this function, and now I'll store this result into. So now what you get out of this is, I mean, what you get out of this is dependent on how you specify the output you want. What I mean by that is that these 2 equations are equations in x and y. It means 2 unknowns and 2 equations, and a is a known constant, but we are providing that as a variable to symbolic toolbox. But since these equations contain x and y, and now the way I'll get its output like this: solve x and solve y. is equals to solve, I'll get solution of x and solution of y. Now it will solve for x and y and consider a as a constant. Okay. So I mean, this is the case. So it understands that a is a constant because I've specified sol x and sol y to be the case. And then let's see what happens. So see, now it is giving out a0 and 0 minus 2a. What are these? These are two solutions. So when so one of the first solution is that sol x when x is equals to a and y is equals to 0, and another solution is 0 and minus 2a. So these are two solutions to these x and y, and a, as you can see, it is kept as a constant here. Okay. So so now we'll move a little bit ahead to the a little bit more number of equations, and you'll get to know how you can solve for three variables in three equations and how to extract the solution matrix out of them. Now let's define another symbolic view v and p, and now what I'm going to create is something called as solution structure. So the background is sol x and sol y. These are the things I used because these will be the solutions to my differential equation. But what if I have like 10 and 15 or 15 differential equations, and for those 15 differential equations in these square brackets I'll have to go on specifying sol x, sol y, or let's say sol 1, sol 2, sol 3, sol 4 up to sol 15. So since it is cumbersome to write that, we'll proceed by writing this s or structure. I mean, this is my own variable. S is equals to solve. Yeah, the same. No, so there are different equations. I've written them down. U square minus v square is equals to a square. Okay, let's create them. U square minus v square is equals to a square. Okay, then u plus v is equals to 1 plus v is equals to 1. Then a square minus 2a is equals to 3. Okay, so now there are three variables. Sorry, b. It should be b here now. B square minus 2b, b square minus 2b is equals minus 2b is equals to 3. So let's just quickly copy. Control C, comma. Okay, the lines. Okay, so now it will be stored. The solution will be stored in the structure form in S, and now it depends on what you ask S to give. So if I put S dot U, it will give me the U values. It will, if I put V S dot V, it will give me V values, and if I put S dot B, it will give me B values. So first, let's understand what it displays. So see, it is giving me a structure with fields. There is a field B field, U field, and V field, and it is saying that it is a symbolic field with values. I mean, it's a 2 by 1 array. I mean, all three are 2 by 1 arrays. So you can see that there are two solutions, because first element of every will create one, and second element of every field will create another solution. So now let's see S dot B, S dot U, and S dot V. See, answer of this. Okay, so B is -1 3. So now if you can see that -1 1 and 0 is one solution. 3 5 and -4 is another solution, right? So now there is a method of taking this and putting this into. So if you want to concentrate on only the first solution, so we'll create a solution matrix like this. Solution matrix is equal to, I'll just put all of these together, B, and now you can see that since these are arrays, now I can index them. So s dot b of 1 space s dot sorry, comma, s dot u of 1 and s dot v of 1. Okay, so solution matrix. So now if you see, so minus 1, 1, 0. So let's comment this. Now, how will this be useful for you to create solution matrix is when when there are number of equations, and you want to find out all the solutions and concatenate them. In which case, you can run this in the for loop, as we have seen, and use iterator variable here, and just keep on concatenating these solutions to each other. Okay, so suppose you want to design something, and that I mean that you're trying to prove something to someone by using all these solutions. So suppose there are 15 solutions in your case, and you want to do some mathematical operations using all those 15 solutions, and you want to compare them. So in that case, you would want to loop through all these solution matrices, and create one solution matrices inside one iteration, solve it, do your mathematical stuff there, yeah, give out its results. Let's move on to second iteration. It will take second values, I mean second solution, and so on. This is how it is useful. So I think that's it for symbolic equation solving. So if anybody has doubts, please go on. Let me save this. Anybody?
What happened when you didn't write 5, 6, and 7 line?
Let me just a minute. Where it disappeared? Let it pop back up. Yeah, line which one?
5, 6, and 7 line.
So I just commented them, no? So sorry, put a semicolon there. So that is why the output is suppressed. See, now it is only showing solution matrix. Okay. Anything else? Okay. So we'll move on now.
Is
We'll
s
now,
dot b some kind of syntax or what?
yeah. So s dot b. So C structure is another data type. So we saw that there are there are characters like B is an alphabet, so it's a character inside MATLAB. So there are number one is a number inside it. So numeric values, alphabetical values, these are all that data types inside MATLAB. So matrices, arrays, cells. So similarly, S, whatever we are getting, is a data type, structure data type. So in that structure data type, a syntax is defined within it, in which if you put a dot and B, it will give out the required values.
Sir,
Yeah.
I'm doing exactly the steps which you are doing right now. But when I'm putting the values in the code, it is again and again it is showing invalid expression.
Where have you put exactly the same thing, same differential equation? You might be missing some bracket or
Yes,
something,
sir.
or equal to signs, double equal sign.
So I have double checked it in the previous takeaway file also, which you were
Okay.
doing 20 minutes before. When I'm putting my codes in my code box, it is
Uh-huh.
showing invalid expression. So can you help me out?
What you can do? See, I need to see the screen to be able to solve this. It is definitely a syntax issue, but I need to see your screen. But I don't think it is not possible. It is possible right now. So all of those who can, I mean, who have those issues like the syntactical issues, I would suggest putting your screenshots onto WhatsApp group. So we'll look at them.
Okay,
Okay.
sir. Thank you. Yes, sir.
And yeah, I also recommend putting clean screenshots of that so that it is visible clearly to me. Sometimes I saw that I wasn't able to see what. what the issue is. So I'd suggest putting up clean screenshots, descriptive one. So so Nikhil is saying that I got the same value screen is showing. So yeah, so there has got to be some some minor missing point in your code in your case. So we'll see that. So we'll now
Okay.
move on. Okay. So now let's see what OD45 is. I think this is it for a takeaway as to save and create another file. Three. Yeah. So OD45 used for the numerical differentiation. You will use OD45 for finding out the solutions to differential equation. But since you're all coming from gate, you have cracked gate now. You know this different, trapezoidal rule. So maybe that's because of for numerical integration. But you know Rangakutta method and all, fourth order, second order. So this is the algorithm will be inside it. OD45 is just a name given to the function. It has been simplified for you, and you just have to provide the function to it, the range to it, and the initial conditions. So what the syntax is like this. So first, I'll first explain the syntax. So it's like this: t, y. I'm taking an example. OD45, OD function, t range, t span, or what we call as t range, time range, and initial conditions y of 0. Okay, so imagine that there's some dy by dt equal to something. So you remember that for a differential equation, you need to do something called as f of xy. I hope you remember this. F of xy, I mean dy by dt is equals to f of xy. Sorry, dy by dt, is equals to some f of xy you were doing, and then you used f of xy into your Rangakutta fourth order method and you solved it iteratively. So that is what we are going to do here. We are going to define a function, ODE function. What this argument means is that we are literally going to create a function .m file or maybe an anonymous function. I'll also explain what I mean by that. We'll create a function and we'll supply it to this ODE45 from tspan and y0. So now let's get to the actual coding. So now we'll first define, let's say for ODE45, let me take one example. Let me take an example. Differentiation. Wait a minute. Creating function handles. Where did I keep the differential equation example? Just a minute, okay. Yeah. Okay. So right from starting with the some simple difference. So so you might not be familiar with the fact that these solvers, or at least ODE45, is meant to be meant for solving only first order differential equations. Okay, first order ordinary differential equations. So if you have got higher order differential equations, we can convert it to first order ordinary differential equations. I'm not sure if you're aware of this, but there is a way of doing that. If maybe the time permits, maybe we can do that. But I don't think I don't think we will have time to see how do we convert it. where it is purely mathematical knowledge of how do we convert a second or higher order differential equation to linear one. So what we will do is first create a function. What we will do is let's create a function. Where is it? Okay, so what I'll do is I'll just use something called as van der Pol equation, or not van der Pol. Van der Pol is actually pretty difficult one to program. So that's one other differential equation, and it's like this. I'll write this down. Okay, so the differential equation is like this: d2x by dt square. Just a minute. Give me a minute. Timeout. Okay. Where is it? Yeah. So the differential equation is this: d2x by dt square, d2x by dt square plus 5 into d2 dx by dt dx by dt minus 4 into x into 4 into x is equals to sine of 10t. Okay, so this is the differential equation you want to solve, but as you can see, this is this is a second order differential equation. So actually it would be first better to solve first one of the linear first order differential equations. We'll keep this in the memory itself. So first we'll define a very trivial differential equation, like let's say y is equals to t square. Okay, so this is so I'll create a function. So before I create a function, there is also one thing that you might have, I might have missed to mention about the function handles. So function handle is like, so let's say you are creating some function. So whatever we created, right, convert b to d. So convert b to d dot m is a function name that we have given, and there is something called as @identifier. So this is called an identifier for function, which will create a handle for a function. So if I write convert convert b to d, where is the exact name? Uh, Function handle. So yeah, convert b to d. So it is showing me here. Okay, so convert b to d, and if I see, let's say c. So c is equals to convert b to d, it just creates a function handle. That means this c, when I call c, it will point to this function. Very simple actually, but just that it is useful in supplying this to some functions like OD45, in which this is given as an argument. So now we'll define an actual function. So let's say uh, let's define one function and something called as anonymous. So is also used somewhere where you don't have to explicitly program a function. So for example, in our case, if y is equals to t square is the case. First case, let's say y is equals to t square. So now, since OD function is something that takes a .m file or function inside, so what we can do is use @ symbol or this identifier to create anonymous functions. That means you don't have to just go on outside and create a new MATLAB function file at all, because it is so trivial. So y is equals to t square, so you don't have to create that. So how you do that is like this. So let's say t square is the function name I'll give. T square is equals to just followed by into bracket then the arguments of this function. Okay, so t square, so t is your argument or the variable. So into bracket t, and now I'll define the function, that is t square. Okay. So now let's say so t square we defined. So now t square is a function handle. What I mean by that is I directly can put OD. I mean in the place of OD function, I can directly put t square, and it will understand what is to be taken inside. Okay, so it will take automatically the square, and you don't have to define some dot m function. But in case of complicated ones, like what we will see for this d2x and dt square and some other differential equations, you will definitely need a .m file separately, and then you will refer to that .m file while you're putting the argument into this OD45. So now t square is equals to @ t followed by t square. I created a function. So the function is now ready. Now I need to give tspan. So tspan is a vector that will ask you for when from which point to which point you do want to solve the ODE. So you might have known from the differential equation that it is not going to give you, it is this numerical differentiation does not use theoretical or analytical approach. So it just solves within a particular interval. Okay, so you already know that. So it needs to be given this information. So what from where till where it needs to be integrated. So we give a t-span in form of vector, and let's say 0 to 6, let's say. So I created a t-span, I created a function. Now I need initial conditions. So initial condition is, so you were also giving these initial conditions, right? In Rangi Kutta. So y of 0 is equals to 0 we are giving. So again the same thing I'll do. Just a minute. Y of t square. Yeah, so initial condition I'll give y of 0 is equals to 0. Y0. So y0 is equal, so I'll create a variable y0 is equals to 0. And when it's applied to this, it will automatically recognize that the initial condition is 0 on y. This is the dependent variable. Okay. So let's write this. T comma y is equals to OD45. OD function. What OD function I want? T square. Comma. What t span? I wrote this t span variable and y0. And it will create. So what happens, you know that y and t, these are two. So t is the independent variable and y is dependent on it. So when OD45 is solved, what happens is it creates a y vector which contains the values of the equation, values of the differential equation computed by it at different times t. So I hope you're mathematically aware of this. So basically what this OD45 will give is not a solution explicitly what MATLAB gave. That's called a closed form solution. What Symbolic Toolbox gave us was a closed form solution in which we literally got a symbolic answer to that. But here we will not get any expression. You're just going to get a data. So T and Y only contain vectors and matrices. So T contains a lin space from some initial condition. So t span goes from 0 to 6, and inside this ODE function it is written for t to be expanded from 0 to 6 with some linearly spaced points. So it may be going from 0 to 6 with step size of 0.0.01, so 0.01, 0.02, 0.03, and so on. And then the y values will be computed at those points. Okay. So now primarily this y vector will be used. So there's no point in just showing you the y values. So what this basically is useful for is for creating this thing. Sorry, plotting. So we'll now also use the plotting command. I'll suppress the output and I'll plot this. Plot t comma y. Like we plotted x comma y, I'll plot t comma y. And let's run this. Okay, there's some issue, too many input arguments. Sets argv1 to type y0. function handles used. Let's just use @t and see what happens. Uh, Let me see. Yeah. I think I failed to specify that there are two variables I'm talking about, right? So t and there's y also. Very sorry. So now it completes the differential equation, right? It doesn't it didn't know what I mean. How come it was asking like how come there is only one variable? So that is why I mean that is where I was failing to provide the second variable, that is the dependent variable. So now @t comma y, and also I forgot to do that here. It's because t square is equals to t. Whatever I'm doing is I'm defining a function. So what I would have defined with the explicit function dot m, I would have defined y is equals to t square, right? So that means that I was talking about two variables. So inside these parentheses, whatever you're talking about, whatever your variables you're talking about, that should go inside. So ty and ty, now it will run. See, it plots y is equals to t square. So it the differential equation was dy by dt is equals to t square, and it's and the difference and the solution to this is this one. So it is what is shown in the figure. Okay, is that fine? Anybody? There might be doubts in this, so go ahead and ask those. Anyone?
Sir, in line 1,
Yeah.
what that syntax means, @ty and then giving space t square.
Yeah. So @ is a @ is used for creating function handles. So there are
Function
two.
handle.
There are. I'll explain. I'll explain. So there are various uses of using @ symbol. So when I'm creating @, I'm actually trying to define a function, and what that function is, this y is equals to t square. But what I would have required, I mean, if there was no such @ thing, what I would do is this: I'll create a new script, I'll define the function, and then I'll create y is equals to some function. I'll have to give the name to it. Let's say squaring, and out input some value of t. Then I'll create y is equals to t square, and then that's it. So this is what I would have created for a function. But then it becomes a little bit this seems like it's very useless to go ahead and create a name for it, explicitly create another file for it and then referring to it. So sometimes what happens is that you don't need this kind of explicit creation of MATLAB files. So in that case, you can just create a function on the fly. So this is what it is called, creating function on the fly, in which case you just @, which means you're starting a function. In the bracket, in these brackets contains the values of, I mean, the variables that you're going to operate on, t and y, and then the syntax of your function. So this y is equals to t square, it is written by this.
Okay. And what's the use of this function handle? Can you briefly
Function
tell?
handle. So function handle is like calling a name to it. So t
Oh,
square is a variable. It's also a variable, right? T square is a tsqr is a variable that I created, and
yes.
I didn't go ahead and created any file and gave a function name to it. I just told the MATLAB that this is the function I want, t square, and give a name t square to it that I will specify it later on. I mean that I will supply to a function later on.
Okay. Thank you.
Okay. So it's like creating name to this function that you want, and then specifying that name, variable name, into the function that you want to specify in. So now this was for the trivial case of just one, this kind of a differential equation in which dy by dt was just t square.
Hello.
Yeah.
Uh, if my question is in line with what the other person has asked. If the definition is given in line 1 itself, like
Mhm.
function is t square, then why do we need to put t square again in line 4? I mean, in the ODE
No,
function.
yeah, okay, I forgot. Yeah, I can remove this. I was just, during the error, I modified it. So now you can get the same thing. See,
Okay.
and you can also do the other way. Like for example, as I said, even if I mean if my, let's say, my code is very long, and I don't want to introduce another variable name. So what I can do is just comment this. So I'll just put this and comment this one. It still work. They there itself. So I'm not even creating a variable. I'm directly defining it there itself. Okay. So this is also you can do. So now actually we will move on to the complicated differential equation. But for that you need to know how to convert this higher order differential equation to first order differential equations. So if there are two, if there is one second order ODE, then you will get two first order ODEs. Is anybody familiar with this? Is anybody familiar with conversion of, say, higher order ODEs to first order ODEs? Just put a yes if you don't, if you indeed have some background in this. Put a yes in the chat box if it is there. Otherwise, there will not be any point in that, explaining that, because it is a longer procedure. But I will just manually show you how it is to be done. Okay, so no responses. So I presume that, okay, nobody knows about this. Okay. So now let's get to ODE 45, this one. So how do I explain you? d2x by dt square. Okay. So now note that this is ODE 45 and it needs a specific form of the function. So you also know this from your previous experience with numerical differentiation while you were studying Rangekutta, that dy by dt is equals to f of xy is the form that this numerical solver will want from you. So if I have this differential equation d2x by dt square and all, this is not at all in this form, dy by dt is equals to f of xy. So now we need to rigorously go ahead and convert it into this first order ODEs, in which we can have this kind of form, dy by dt is equals to f of xy form. So how we do that is like this. And I'll try to explain you with, here only. So with this differential equation, what we can do is just substitute x1 is equals to x and x2 is equals to x dash, its derivative. So now after defining this, take derivative of x1 dash. So x1 dash is equals to x dash and x2 dash is equals to x double dash. Now if you see, x1 dash is equals to x dash, which is actually x2. So x2. So now remember this as an equation 1. And x2 dash is equals to x double dash. Now I'll go on and see this one. So this, in this differential equation, this basically means, this also means x double dash plus 5x dash minus 4x is equals to sine of 10t, right? So this is the differential equation. Yeah. So this is the differential equation. So now I can just find out x double dash from here. X double dash from let's say, let's call this equation 2, and this is equation 3. Sorry, equation 1. So from equation 1, I can directly find out x double dash is equals to sine t. So minus 5 of xt minus 5x dash plus 4x plus sine t and 10t. Okay. And now this is the differential equation number 3. So now x dash is just a minute. X double dash is actually x2 dash. Okay, so see, these are the differential equations. dx1 by dt is equals to x2, and dx2 by dt is equals to minus 5x1 plus 4x plus sine 10t. So this is mathematically, it seems very correct, and it is actually. There's no question of that. But this is how ODE 45 will solve these two equations. So whenever you come across higher order differential equations, you need to convert them to to couple of first order ordinary differential equations, and then since solving these two simultaneously means exactly solving the parent differential equation, you will get the same result. And the rule is that if it is a third order differential equation, then there will be 3 first order linear ordinary differential equations, and so on. Okay, so this is how the conversion is, and now we are in position to solve this inside this ODE function. So now how I can write this. So let's see. Maybe what we can do is use another script and define this function dx dt. See, you also need to remember that dx1 dash dx1 by dt and dx2 by dt, these are just two differential equations that we have created from the same equation. Okay, so it doesn't matter what x1 dash and x2 dash mean. It's just that whenever you come up, so let's say you might see that since I introduced x1 and x2, there'll be two variables. Well, yes, when the ODE function ODE 45 gives you values, it will give you in terms of x1 and x2 dash, or x1 and x2, but you know what x1 and x2 is, right? So you will get values in terms of x1 and x2, but you know x1 is this and x2 is this. So you can easily you get your information from this file, this function. So let's create a script file where I will define this function. Where is it? Yeah. So no, not an MLX. Let's create a new script. So function I'll define. Let's say dx it is dx dt, right? Dx dt is equals to RHS, because RHS is our ffxy. RHS, which will take t and x. Okay. So now, as per this first equation, dx dt underscore 1 is the variable I created. Dx dt is equals to x of 2. Why x of 2? Because now x is a variable which contains x1 and x2. Okay, right? So x1 and x2 are the two variables that I'm going to use now because we converted them. So x2 means I mean x of 2, which means I'm referring to the vector x, but the second element of it. Then dx dt underscore 2 is equals to, again, minus 5 times, what was it, x2 plus 4 times something x1, x of 1 plus sine of 10t, 10 into t. Okay, and now what I need, so OD, according to what the OD function, or so OD45 demands, dx dt, or the differential equations. If you have a set of differential equations, then you have to put it into an array. So I'll define an array here, dx dt array, which is dx dt score 1 semicolon dx dt underscore 2, and this is how I defined the array that will go into the function. Note that this dx by dx dt is our output variable. And we have to note that whenever you're creating a function, whenever you define this output, this should be, I mean, at the end, whenever the function is complete, this should receive some value. So if I create let's say function total is equals to add two numbers, num1 and 1 and 2. So if I create this function, then I need to I can do all sorts of fancy stuff here, but at the end there should be something to reference this output variable. So tot is equals to n1 plus n2. This case it's very trivial, but this tot should be referenced. If it is not, what happens? See, the function return value tot might be unset, and this is warning you that even if you call this, there's no point because it won't output anything. If you haven't set the value of tot in the function, that what tot should calculate finally, if you don't set that, then there's no use of this function. So that is what I wanted to tell you quickly. So dx by dt I'm referencing here. Dx dt are two variables I created, which were, where it is, x2. So dx dt1 is x2 and dx dt2 is this equation. So now how does it differentiate between these two differential equations? It doesn't have to. It just knows that it needs, if there are two differential equations, then both of them will be in this form. So when I'm supplying it in this array form, when it gets inside, when it is being supplied to ODE45, it detects that this is one differential equation and this is another. And we want that these two differential equations to be solved simultaneously, and after that we'll get our solution. So this is what ODE45 is going to do for us. So I defined the function dx dt is equals to RHS. This is our function name, and now I'll save this as the same as the name RHS.m. I saved it. Now I'll call this another script where I'm using the OD function. So now what I'll do is this. I'll set as this, so you'll see in clear, so as to get a clear view. Then I'll create, so remember that it requires a function that we've already provided. Then it needs a t-span. So let's create a t-span, which is, let's say, I think let's 0 to, I don't know, 0 to 3. Then what it will need is the initial conditions, right? Is the initial condition x. So I forgot to mention the initial conditions while I was providing the differential equation, and the initial conditions like initial x. So init x is equals to 0. So that means dx by dt, so x double dash is x double dash plus 5 x double dash x dash. minus 4x is equals to sin t. In that case, x is equals to 0. X of 0 is equals to 0, and dx by dt is equals to also 0. Init dx dt is equals to also 0. So now, even if this is not understandable right now, it will become clear in a while. So now I'll create t comma x is equal to OD45 at the rate RHS RHS comma span comma y0, in which case I'll specify it in an array init x space init dx dt. Okay, so that's it. That is the OD45 definition. And yes, now we'll have our solution. Let's see, first save OD45. No. So solving using OD45. Okay, now I'll just run this. Let's see what happens. Command window. Run. So yeah, it is. It has. It. I mean, the running execution is complete. Now we need to plot it to see. So there will be x values, right? So now let's plot it. Plot t comma x. Okay. So these are the two variables that. Okay. So x. Okay. So x is the what I can say. X is a vector, right? Because x is a matrix because x, as we have defined above, that x contains x2 and x1, and what x2 and x1 are we have defined earlier. But in a sense, x is a matrix that contains in its first column values of x1, and in its second column it contains values of x2. So if I specify by indexing just the first column, or since it's a matrix, I'll use the notation that I want all the rows of the first column. Okay, so we get this. And if I do, okay, so if I do specify g plus hold on plot t comma x, everything from column 2, nothing. Okay, so what you saw before, just in different legend. So this is how you get the equations to solve. Now there will be questions like, what is this init x is equals to 0, init dx dt is equals to 0. Now you need to know the insights of OD function, OD45 for that. Now this will you will get to know when you will actually be introduced to this mathematical rigor of converting a higher order to linear orders, and how these simultaneously solved, how these two first order differential equations are solved. If you know that, then you will get to know what this means. But roughly, it's like this. I'll tell you. I'll try to tell you. So here, as we first created an x1 and x2, so x1 dash is equals to x2 and x2 dash is equals to x2. These are two differential equations I created. I don't need to specify MATLAB that these two belong to same problem or not. I know mathematically that these two equations belong to the same problem, and if MATLAB solves them simultaneously, I'm going to get the solution. Okay, so x1 and x2 are my two variables because I'm talking about two differential equations here and two unknowns. So since these are simultaneously being solved, I'll need two variables and two equations. So x1 and x2 are the two variables of it. So I created the variable x as a vector with matrix with two values, two kinds of values, the x and x dash value, depending upon how I'm specifying this. Okay, so I created an RHS. Where is it? I created an RHS or a right hand side of this function in which I specified that dx dt1. So the first differential equation is this, the second differential equation is this, and then dx dt is equals to this. I mean, just created an array of it because ODE45 wants this, wants it in that form. And initial, I put down the initial conditions. So what these initial conditions will do, automatically it will assign it to first that is x1, and this it will assign to x2. Okay, so x1 is equals to 0 will be assigned and x2 is equals to 0 will be assigned. So whatever I'm doing here, this is my own formation of my own variable. It will not understand what I mean by this. This is for me, but whereas inside, since I'm putting up RHS, and since x is a vector, so since x is a vector, it will assign automatically init x. That means x1 is equals to 0, and this says x2 is equals to 0. And we know that x1 is equals to 0 means x, and x2 is equals to 0 means x dash is equals to 0. And that is how we supply our boundary conditions to the problem. So now, any questions? I think there will be having some questions. Anything?
No, sir. Why we have defined x1 and x2 equal to x and x dash?
Where is it in this? In this?
Yes.
Yeah, that is how we create that is how we convert a second order differential equation to first order differential equation.
So
This is
xn.
this is just a mathematical substitution. If you look at it, I just created a variable x1, which is just x, and x2 is equals to x dash, the differentiation of it.
Okay.
Okay, and just I'm using those variables to denote the two differential equations that I will solve using OD45.
Okay. So x1 and x2 are values, or means we have to solve with this.
So since x is a variable, you know x is a variable. So I created x1 and x2 as x1 and x2 variables. So initially I had one variable, but since it was in a second order differential equation, I couldn't solve it with OD45. So I created two variables so that I can solve it with two differential equations. Okay.
Okay.
So imagine this is like you're solving one of the major or complicated equation by converting it into a couple of simple equations. But then since if you're going for two differential equations, so the two unknowns for two differential equations. So since it is accepting two differential equations, it needs to know that what is the variable in the first equation and what is the variable in the second one. Okay.
Okay.
Even if you don't understand this right away, don't worry as you solve more and more applications, because I think for anyone, if anyone is there from mechanical, he will notice that in vibration engineering subject, I'm talking a little specific, but in vibration engineering, this will be used a lot. So OD45, in which you'll be taking, so for example, mx double dot plus cx, so c plus cx dot plus kx is equals to some function, is a second order differential equation. So in that case, we'll have to use this conversion to plot it. So yeah, so it will be used ahead. Even see, this is so what I was talking about is the spring, but this is also applicable to electrical students, which is used as exact form, but harmonic. I don't know. There is the same form actually. I don't remember the exact thing, but it's like LDI by dt and stuff. So basically, we have this analogy between the mechanical spring damper system and LCR circuit. So the same equation actually forms up, and you will use again the same thing. What if we don't have initial conditions, but conditions somewhere in between span t? No, so this you're talking entirely about different method, right? So OD, so what? So if I'm OD 45 solver, I am demanding you to give me initial conditions. So basically, in your Rangekata method, you are giving it initial conditions. So that's why here also you are giving the initial conditions. Did I answer your question, Kaushal?
Yes, yes.
Okay. Anything else? Will just move on. Last couple of minutes left. I'd advise not to leave directly. I mean, wait for at least a 5 minutes. I see attendance dropping sharply after 12:30. I know. I mean, okay. So this is the last day of the workshop. So hang on there for 5 or 10, maximum minutes. Don't just leave. Okay. So after OD 45, I was planning to complete about so give you something about linear programming and a LSQ curve fit. So I'll quickly go on and do that too. So let's get rid of this. This is entirely okay. This is now a new thing, that is this linear programming. So you obviously know the linear programming concepts. Okay, so now let's see. Linear programming. Okay, so F stands for objective function. Whatever your objective function is, then A and B and AEQ, BEQ. Have I written this? No, sorry, I didn't read down. Let me write this first. So linprog, linear programming. So in linear programming, you know that there is. So I'll just directly write down F is an objective function. You see use of F ahead. Then A and B. For now, just remember that they are matrices and vectors. Matrix, vector corresponding to uh, inequality constraints. And AEQ, BEQ, matrix vector corresponding to equality constraints. UB, so LB, UB, lower bound, upper bound. Okay, so this is how we will see now. So the syntax is like this. So let's say X is equals to linprog, linear programming, some function F, A, B, AQ, BQ, and there are some more of them. AEQ, BEQ, LBUB. There is something more, I think, with the help of options. Something called as options. But you can, so you note that these are not compulsory arguments. Even if your problem has F, A, and B, you're still solving a linear programming problem with inequality constraints. And that if your problem doesn't have any equality constraints, you can just leave them blank, or just use this much part. You can use that. So now I'm just jumping ahead a little bit so that you'll get an idea of the entire the spectrum of what kind of solutions we can solve. So now, okay, so there are a couple of constraints, equality constraints and inequality constraints. And what I'll do is I'll just straight away I'll tell you the constraints for what the constraints were and what does A and B mean. And for that, I'll also have to create an objective function. And for objective function, also there is some method. Okay. So this x, size of x, depends upon how many variables are there. So in linear programming, if you might have gone through this very common style of programming in which there will be x1 and x2 variables, and you have to minimize some objective function. Let's say some ax1 and bx2 plus bx2 or minus bx2, subject to some constraints on x1 and x2. So this, but depending upon how much variables you have in your objective function, the size of x will be corresponding to that, and it will take up that size automatically depending upon the f. So now I'll go on and define f. Why I defined f like this, I'll let you know. -1 by 3. What I mean by that, it just means this: f is equals to -1 into x1 minus 1 by 3 1 into x2. There are two variables, x1 and x2, and the coefficients I've written inside this -1 and -1 by 3. Why? Because this is the demand from the linproc command or linproc function. That is why I defined like this. Then what I'll define is, now I'll need a matrix. So what A is, I'll write down first directly, and A is 1 1. Sorry. Just a minute. A, yeah, A into X less than 2. Yeah, okay. So I'll write down A. It's like this: 1 1 minus 1 1 by 4. 1 1 by 4, 1 minus 1. 1 by 4 minus 1 by 4 minus 1. 1 minus 1. Minus 1 minus 1 and -1 1. I cannot take random values here because so we might not land up on the solution. So A is this, B is this. I'll tell you in a minute what I mean. 2 2 1 2 1 2 1 2 1 -1 2. So what A means, it's this. It's just that these are constraints. X1 plus X2 is equals to 2. X1 plus X2, X1 plus 1 by 4 X2 is equals to 1. X1 minus X2 is equals to 2. So it's like this: if you multiply A with the vector A with the vector X, you'll get B. Sorry, less than B. It says, since there are inequality constraints. What we have programmed here. So when I'm being given these set of constraints, like in the form of equations, I'll convert them into matrix form, and you know very well know that how do we do that? Just take the coefficients in the matrix in the matrix form and multiply it with the vector, and you'll get, so yeah, so you'll get the x equal to b. Now the only so the only issue I seem to see here, according to the objective, is the fact that it is to be supplied. I'll see why. Save. What is this len programming? Okay. So now, okay, so since I've got f a and b now, so why I wrote this I'll explain later on. This is a syntactical condition. Then I defined f. Then I have my inequality constraints. Now I'll have some of the equality constraints. It's like again the same thing. I'll define aeq is equals to 1 by 4, and beq is equals to just 1 by 2. Okay, so it's like x1 plus 1 by 4 x2 is equals to 1 half. This is equality constraints, and this is like x1 plus x1 plus x2 is less than or equal to 2. X1 plus 1 by 4 x2 is less than or equal to 1, and so on. Now we are in position to, okay, so we'll also create some lower bound and upper bound. So let's say my lower bound and upper bound on -1 and 1.5 for x1. LB lower bound. Note how I'm specifying the lower bounds. Lower bounds for both variables. I'm specifying lower bounds for both variables. So for x1 it's -1, and for x2 it's -0.5. Whereas upper bound for x1 is 1.5, whereas for x2 it's 1.25. Now let's use the linear programming function. S is linprog f first, then a, then b, then aeq, then beq, then lb, then ub. And what the options is, we'll see later. So let's execute this. So let's see what happens. Optimal solution found. What this is? See, this is the optimal solution it found directly. 0.1875, 0.125. Okay. So what this options is also also explain and about this. So just a minute. Let's try a little. I don't think it will work, because even if I said that, because b, if you see, b is actually this thing is, it's a row vector. So 2 1 2 1 minus 1 2. So I don't think this will work. This will give me a syntax error, I think. No, okay, it didn't. Okay, so no. So this was correct. So ax equals to b. That it also means that you can specify a matrix like what we did before. Now see. Now we'll see. Yeah, no. So maybe some students also see this kind of error, right? I mean, all those who are asking for doubts, maybe they are seeing this error, invalid expression check for missing multiplication operator and stuff. So okay, I'm very sorry. I was not familiar with this syntax of, just entering this, just writing this on a new line creates another vector. So another, and just putting it down below one row. I wasn't familiar. It creates another row. So you might as well learn this right now. That 1 1, enter 1 1 by 4, enter 1 minus 1. Actually, are creating different rows into itself. So I was under the impression that we can only do this syntax. Okay. So I'm sorry for not explaining you this before. I was experimenting right now. So yeah. So this is the way you supply it. So you know how ax equals to b was, you know a equals to b equals a lower bound, upper bound, and now we'll see what options are. So options is when you can specify which algorithm you want to work with. So there are a lot of algorithms available. So out of which I'll just specify one of those, and that is the interior point algorithm. So what I'll do is create an options variable. Options is equals to optim. No, I think it's optim options. Optim options. So optim options will specify what it is. It is linear programming. So optim is a very higher or broader toolbox into which there are lots of variables. Sorry, into which there are lots of toolboxes inside. There are lots of functionalities, and inside that we are just referring to linear programming. Then algorithm. I'm trying to tell it what algorithm to use, and I'll specify in the next argument what is to be used. So I'll use interior point. Interior point. This is the name of the algorithm, interior point, and that's it. And now I'll provide options as a variable, options as an argument here. Where is it? Yeah, run. Okay. So the same thing actually. I mean, this is since this is a very trivial problem. Interior point. There is interior point algorithms. There is sequential quadratic programming. There are lots of such optimization algorithms available, and which depend. I mean, the usage of each depends on the condition of the application. So actually, we don't have enough time. Otherwise, we would also have gone through what are the conditions. But it's very specific to to your own domain, and maybe on the WhatsApp groups, we'll stay on touch, and I'll provide some resources for you to learn where I mean from where you can know which to be applied to what. So interior point again, interior point was not necessary here, but how do you know that where to use? So there is entire set of documentation available for that. Well, in the WhatsApp group, I'll provide the links to all these documentation and further learning. So this is for linear programming, and there is also one more function left, LSQ curve fit, which is again very simple actually, and maybe we don't have enough time for that. The time has run out. So what we can do is so about linear. So LSQ curve fit, I'll provide what I wanted to say, what I wanted to tell you in form of a in the form of a text file and post it on the WhatsApp group so that I can read it on later. Okay, so I think this is it from me for the whole session, for the whole MATLAB workshop. I mean, this is at, I mean, what I mean by that is this is only from me. Yet there's infinite knowledge out there regarding MATLAB, and you are encouraged to find out more and more about it. And you will find out more and more as you go into application of your domain knowledge. So there are lots of apps available here, like optimization, curve fitting. Out of these, only some of them are actually extensively used in the industry. For example, this deep network designer, neural network clustering, neural net cluster, neural net fitting. These stuff are for machine learning and deep learning, and nobody actually uses these because there are much sophisticated libraries available out there. But mostly curve fitting, distribution fitter, optimization, all these stuff is used in MATLAB. So for example, in signal processing also, these are the tools you will use, and you'll get to know how to use these tools as you go and apply. Because I was also going to cover optimization, but since optimization will require some sort of domain knowledge, uh, I'm not covering it. But in optimization also you can find out. I'll just give you a quick view of the window. So this is the optimization tool that you get. This is the solver. You can select between all these. So see, now LSQ curve fit is a optimization algorithm or a solver. Okay, non-linear curve fitting. So among these solvers you can select, and again depends on the application what you want to select. Then the algorithm interior point, SQP, active set, then the objective function, start points, equalities, again the A and B what we saw, AQ, BQ, lower bound, upper bound, nonlinear constraint function, that again you have to specify using function handle. But all of these details you'll get to know when you actually start applying your knowledge. So I think it may be unnecessary for me to cover all these in detail. So that is why it has been skipped for now. You will not be needing that. I mean, not all of you will be needing that. So any other questions if you have, you can ask, and then maybe we'll leave. And regarding assignment submission and all the issues of the M file and MLX file. So I think for that issue, no, but nothing can be done for the people who have already submitted. So for them, I am noting down the roll numbers for for reference. And for those guys who haven't submitted yet, please try to copy paste your code script file, MLX file into a code like this. I'll show you. So just go and create a new script. Take something. So maybe this. So take something from this section. Maybe suppose this was your question 2. So select the section corresponding to question 2, Control C, and put here. Put maybe your CLC clear all stuff, and then save it as save it as one of the .m file. Okay, so that's not that hard. And for the people who are having those problems, maybe they can put their screenshot of the screen, a screenshot on the WhatsApp groups. So I think that's it from me. Akhila and Suraj, what do you think? Do you have anything to tell?
Anybody having any doubts, they can clarify it now. Otherwise, I'd like to say thank you, Soham. You have spent this much time with us. I have clarified all their doubts. So thank you so much on behalf of PGC and from all of us. And thank you all the participants. Thank you all the participants. You have spent this much time with us, and we hope that this was like a helpful session for you all guys. And further doubts, anything you have, you can clarify it with Soham in the WhatsApp group. And the yesterday's recording has already been uploaded in YouTube. And today's session it will be in Teams, and it will be uploaded in YouTube soon. So any of you guys you want to clarify anything, you can ask now.
Yeah, you can go ahead and ask.
One question.
Yeah.
Hello.
Yes.
For last week's sessions, I mean session 1 and session 2, will there be YouTube videos available?
Actually, the YouTube videos are uploaded there, but it's actually not our session. Due to some technical issues, we couldn't upload that. But you can still refer to that videos. It will be helpful for you guys.
Okay, so maybe the basics will be almost the same in all the videos. So you're encouraged to check them out there. And so this was just a short. Even if you have spent around 12 hours, not 12 actually, maybe 11 or 12. Maybe you have spent around 12 hours. But even if we have spent 12 hours, it's not enough at all. So this is just a scratch on the surface. So major purpose of this workshop was to get you familiar with the software, not to explain everything in detail, because even there are some on-ramp sessions of MATLAB that they schedule and even have their videos on YouTube that are much more informative than me. But the purpose of this workshop to get you to at least go to YouTube and encourage you to find them. So what happens is usually the people are not, the people fear this something that they are not understanding right now. But as you can see, it's not that difficult. What matters is your logical understanding and formation of your algorithm. And so, yeah, even if I haven't covered optimization toolbox and all, even I haven't covered LSQ curve fit, it is fine. You will anyway find it out later on. And even if I had covered, you wouldn't remember it unless and until you apply it. So I apologize for not covering the optimization toolbox, but you will still be able to solve, and you will be still able to cover much of it.
Yeah, this like even if we couldn't complete so much vast subjects in this session, but I think this will be really encouraging for them to continue with this and learn more about this MATLAB.
Yeah, right. True. So with this, maybe we'll stop now. If you have any questions, I mean, we can stay in touch on WhatsApp group. Maybe at some point of time, maybe you will help out your classmates themselves, and yeah. So thank you,
One more
Akhila. Thank you,
question.
Suraj.
One more question, sir.
Yeah, Shekhar. Yeah.
Yes. So, can you would you like to suggest any YouTube channel for that MATLAB practice?
Yes, yes. So I will put a link on. So I'll also put I've prepared some some links to be posted.
Okay. Thank you.
So there is something called as MATLAB documentation, and there are MATLAB on-ramp sessions also. So it is highly encouraged to visit them now. Now you'll start to understand them, and some of them will be repeated for you, but those are very helpful sessions there also. So MATLAB on-ramp, MATLAB documentation, and just outright Googling, very helpful. Just form your logic and Google it. Google the syntax for it, and it will right away give you everything. This is the chat. The chat link I've the link I've put in the chat box is for Symbolic Toolbox. You are encouraged to find out more about it. Then there is one more link. Oh my god, there was one more link. I deleted it somehow. Okay, I'll post it afterwards. Okay, so guys, thank you very much. Thank you, Akhila. Thank you, Suraj, and thank you, Saurabh,
Thank you, Soham.
for
Thank you so
your
much.
time.
Yeah.
So we all have devoted a lot of time to this. So thank you for all the work in the background. Thank you to all the people who have shown their interest in learning this stuff. Thank you for listening to me. Okay, so yeah, with this we'll stop, and all the further questions we can take them on WhatsApp group.
Yeah.
Okay.
Sure.
Okay.
Thank you everyone. Thank you so much. Stay safe.
Thank you.